So this is the last topic in Unit 1, and fortunately we missed this in our previous last week lecture. So I'll give a brief introduction to what system model is, and in fact you will be studying about this in in your third year in dynamic system analysis in very detail. So probably I shall be teaching you the same subject, dynamic system analysis, next year, and will be taking this part almost covering a unit there. So we will be briefing about the system model here, and then we'll be talking in detail in next year. So system model, one form of representation is the input-output description. So a system, by system we mean that it could be electrical, mechanical, hydraulic, acoustic, electromechanical, and chemical. This can also accompany the social, political, economic, and biological representation as well. So they all can be talked to be a sort of system. So a system description in terms of the measurement at the input and output terminals is called the input-output description. In fact, by this definition we are talking about the system to be a black box. So when we talk about input-output description, we are concerned with the type of input that we are giving to the system and the output that we are taking from it. So that input-output description description of the system is termed as input-output description, and this means that this type of description will not be talking about the parameters inside the system or any knowledge or anything that is related to something which is inside the system. So for this you need only to know about the input as well as output. So from here we will study in next year in dynamic system analysis what we term the we arise with the concept of transfer function. So transfer function that describes a system is given in terms of the output and input only. So for example, the first step in analyzing any system is the construction of a system model. So this is something that we have experienced, that whenever we try to analyze systems, so there are few approaches that we follow, but the basic approach, the first very important approach in order to analyze any system is to come up with the mathematical description of that system. So that mathematical description may be some sort of equations that represents the dynamics of the system, and thus they qualify as the mathematical model of the system. So a mathematical expression or a rule that satisfactorily approximates the dynamical behavior of the system is a sort of input-output description. So things well, in fact, regarding the mathematical expression analysis of the system, you had been carrying out this from your you did this in your first year as well, and you did in your diploma courses. So this is not something new, but just we will be having a review of what we know, and try to understand that how systems will be modeled using the mathematical approaches. So given here is an example where we are required to find the equation that relates the input to the output, and this is a RC circuit, and it's given that if the input is the voltage xt, so this is the input voltage of value xt, and the output in the first case is the loop current it, and the second output to be considered is the output the voltage across the capacitor C, which is taken as yt. So we will first focus the input x and the output I for the first case, and we'll try to come up with the input and output description, which will in fact be the mathematical representation of the system, where x is taken as input and I will be taken as output. So we start with the loop equation for the circuit, which can be written as R times I. So we simply apply the KVL to this loop, and we come up with the expression. For example, this can be written vice versa by taking x on the left side. So xt, the voltage supply, will be equal to I times R plus 1 upon C minus infinity to T I tau d tau. Or this can be written as, if we further simplify, because R is given as 15 and the value of C is given as 1 upon 5, so this can be written as 15I plus phi integration I d tau equal to xt. Now if we try to replace the integration and differential terms by their operational notation d, so d represents the differentiation, it's the operational notation simply. So the equation can be, this equation can be expressed as 15I plus 5 1 upon d I t equal to xt, which is written here. So 15I plus 5 upon d I equal to x. Now this can further be simplified as 15d. So if we take the we take d on one side, we cross multiply it, so what we are left with is 15d plus 5, and I is taken as common here, and then d this will be equal to d times xt. And we again, since we use d as the operational notation, if we again replace this by its original notation, that is d by dt, so this can be written as 15 d by dt of I plus 5I equal to dx by dt. And since I can be written in terms of the voltage across capacitor as I equal to C dV by dt, or since voltage across capacitor here is taken as y, so this can be written as I equal to C dy by dt, which is equal to 1 upon 5 dyt. And if we substitute this value of it, 1 upon 5 dyt, into expression A, so what we get is 1 upon 5 here, so 3d plus 1 yt will be equal to d times xt, and the term if you take d by dt of the term d and d cancels out, so if you are going to have dyt in place of it, then the d that comes here will be cancelled out with the d on the right side. So what we are left with is xt on the right side, or this can be written as 3 dy by dt plus yt equal to xt. So this is, in fact, this equation represents the mathematical model of the RC circuit when the current I is taken as the, so this particular equation, this one, which represents the relation between I and X, gives the input-output description or a mathematical model of the given RC circuit, where I is taken as the output and X is the input. While if we take Y as the output and X as input, this particular equation represents the input-output description or the mathematical model of the given RC circuit. Now there was one more topic that was left during the lecture, that was related to the plotting of the, or sketching of the waveforms when we talked about time reversal, time shifting and time scaling. So let us again brief that part so things would be more clear. So we talked about the basic operations that were performed on signal and the transformation of independent variables, taking where we talked about shifting, scaling and reversal in time domain. And we studied about time shifting, how time shifting is done, what is time scaling. And there was one thing that I couldn't talk about. So I told you that during time scaling, what we do is if we have to scale a signal xt to another signal a x of at, so if a is going to be greater than 1, in that case the given signal xt will be a sort of compressed, so compression will be done to the original signal. And in case if a is less than 1, in that case the original signal will be expanded or dilated also. It's also called as dilation. Now the second thing that we talked about was one thing that I missed was while we talked about time scaling, we were focusing on the compression and expansion of the waveforms only, but in fact the compression and expansion of the axis was not talked there at that time. So what actually happens is whenever you time scale a signal, So there is a sort of compression or expansion that is going to happen on the axis, the x-axis as well. So this had been explained in this particular slide. So suppose that we are given a signal xt, and let's say I, instead of taking any arbitrary scaling factor, let us take it as 2. Let's say a is equal to 2. So we are now interested to plot a signal x of 2t. So let's call this signal as y. So yt is equal to x of 2t. So what in fact is going to happen when we are going to time scale the signal x with a scaling factor of 2? So the point, let's for example we have t equal to 2 in case of xt, will be in fact gone to t equal to 1 for yt. And again likewise for t equal to 4 on xt, will be representing the point t equal to 2 on yt. So this is what happens when we are going to time scale a signal with the scaling factor greater than 1. So the axes will also be getting compressed as shown in this figure. Likewise on the left side, if we see that -2 for xt will be compressed and will be represented by -1 for yt. -4 on xt will be represented as -2 for yt, -6 will be represented as -3 for yt, and -8 is -4. So if you look into this figure, what is happening is the axes of xt are being compressed twice. So 2 times compression is being taking place on the axes. So that is what happened when we previously talked about time scaling, that the waveforms which were originally drawn for xt were getting compressed. So that was because the axes were being compressed, and that caused the waveforms to be compressed. Likewise, if we are going to dilate or we are going to expand by taking the scaling factor less than 1. So if suppose that we, instead of taking a as 2, let's take a as half. So now we are interested to talk about the axis for yt, where yt represents a signal x of 2 by 2, t by 2. So in this case, what is going to happen is the axes are going to expand. So for the values of, for example, t equal to 1 for xt, we are going to get the value for yt as t equal to 2. For t equal to 2 in case of xt will be taken as t equal to 4 for yt, and for t equal to 3 this will be 6 on yt. For 4 on xt it's 8 on yt. For -1 on xt it's -2 on yt. -2 on xt will be -4 on yt. -3 on xt is -6 on yt, and so on. So now, as on the contrary to the previous figure, so if we look into this figure, what is happening because of this scaling factor taken less than 1, the axis for xt is being expanded or dilated for the signal yt. So keeping this in mind, we will try to understand the precedence rule or the sketching of the signal while time reversal is being scaling is being done there. So the precedence rule that was left while we were sketching the plot is given as follows. So while sketching, the steps that are followed is, the first step will be time shifting, followed by time scaling, then finally the time reversal. So if we are going to follow these steps, then we are going to come up with the proper sketch. For example, we have a signal xt here, and we are required to sketch the following signals, starting with x3t, which is a simple signal talking only about the time scaling of the original signal xt. So let's start with x of the first signal x of 3t. So for x of 3t, since as I told you that the scaling factor here is greater than 1, which means that the signal will be compressed. And by what factor it will be compressed? So since a is 3, the compression will be by 1 by 3. So the value 1 will be compressed by 3, which means this extreme point will be 1 by 3, and since this is -1, this will be -1 upon 3. So we have compressed the signal thrice. Had this been x of 4t, then the compression of the original signal would have been taken by factor 4. Now we have another signal x of 3t plus 2. So in this case, we have both the things, the time shifting as well as time scaling. So we have to perform, since both the operations are to be performed on this particular signal. So according to the precedence rule, we will be first trying to shift the signal by a factor of +2, which means that the signal will be, so if this is the signal, original signal xt, and we are interested to, so if we have to first shift the signal by a factor 2, +2. So let's call the signal as y1t, which represents the shifted signal xt by factor of +2. So which means that +2 factor means that this original waveform, which is again drawn here, will be shifted towards left by 2 units, like this. So we have shifted the original waveform by 2 units, and the point 0 for the original waveform will now be at the location t equal to -2. And since from 0 we have this point, the extreme point +1 will be -1 here, and for the left extreme point -1 will be t equal to -3 on the plot y1t. So this is the time shifted version of the signal xt, and the shifting had been done by a factor of +2. Now the second step is, after time shifting, will be performing time scaling, and the scaling factor is 3. So this is greater than 1, which means that there will be a compression in the axis as well as, so if you focus on compressing the axis or expanding the axis, then automatically the waveform that had been shown will also be compressed or expanded respectively. So since we are seeing that the factor is greater than 1, so here we will be having a sort of compression, which means that since the factor 3 is used, so this particular point will be taking a value of -1/3. This will be taking a value of -2/3. This point will be taking a value of -3/3. So let us first draw the same waveform here, and now we'll try to compress it, since this is the whole x-axis or the horizontal axis has to be compressed along with the drawn waveform. So now let us compress this. So this is the final waveform or sketch of the signal after compression by 3. So if you look, the value -1 is now taken as -1/3. So, and likewise -2 is -2/3, and -3 is -3/3, which is simply -1. So this is the, let's call this as, this sketch as y2, which is nothing but the time scaled version of y1/3. So this can also be written as y2 equal to y1 3t. So if you substitute 3t in this particular expression, what you get is x of 3t plus 2, which is the original expression of the signal desired to be drawn. Likewise, we have another signal x of -2t minus 1. So here we will be performing the time shift first by a factor of -1, which means that the original waveform will be shifted towards right by 1 unit in this manner. So we have shifted the original waveform by 1 unit on right side, and then we will be performing the time scaling by a factor of 2, and then finally, since we have a negative sign along, which is nothing but the time reversal, so after performing the time scaling, we'll be performing time reversal. So if we perform the time scaling on this particular signal, and since the scaling factor is greater than 1, which means that the signal or the axis, the horizontal axis, will be compressed by the same factor, and the signal would look something like this. So this point, which was occurring at 1, will now be at the location half, while this extreme, which was initially at 2, will now be appearing at 1. So this waveform had been compressed by a factor of 2 and is represented here, and what we get is the signal x2t minus 1. So this is after shifting and compressing, the signal we obtain is x2t minus 1. Now the final sketch will be obtained if we incorporate this minus sign as well. So if minus sign is being introduced in the expression of x2t minus 1, which is nothing but the, what we call it as the time reversal. So the time reversal version of this signal would be something which is nothing but the mirror image about the vertical axis as shown here. Likewise, this is the signal x2 t plus 2, so this can be represented as, this can be simplified and written as x2 t plus 4. So this is necessary that whenever you perform or whenever you sketch waveforms using the precedence rule, so you are supposed to simplify expressions of like things like this. And for example, x2 t plus 2, since t plus 2 is inside the brackets, so we open the bracket, multiply 2 with each of these terms, so what we are left with is 2t plus 4. So this is to be done whenever you apply the precedence rule. There are other methods that exist, so where you don't need to focus on precedence rule, but since you are supposed to follow one set of rules, so that things would be easy. Otherwise you would get confused if you focus on other rules, irrespective if you're very expert in drawing these sketches without the rules. So there are simple methods. I'll explain that. If you don't remember the precedence rule, as I did in my previous lecture, I forgot the precedence rule, but I was able to draw these sketches because of that concept or that shortcut. So if you understand the concept of sketching, then you don't need to learn the precedence rule, or you don't need to remember it. So now, in order to plot this sketch x2t plus 4, we have first of all to time shift the original signal xt by a factor of plus 4, which means that this waveform will be shifted by a unit of 4 towards left as shown here. And after shifting this waveform towards left by a factor of 4, the second is to time scale it by 2. So the whole x-axis along with the waveform will be compressed, and the signal would look something like this. So in order to ensure that the compression had been taken place correctly, so -3 will be, since we are compressing this by a scaling factor of 2, half, then -3 would be written as -3 by 2, -4 will be -4 by 2, which is -2, and -5 will become -5 by 2. Now the second is x2t minus 4. So if you again you have things inside the brackets, so you'll have to open the brackets, and in order to apply the precedence rule, you get this as x2t minus 4. So this is x2t minus 4. You will be shifting the original waveform by 4 unit towards right, then you will be scaling this by a unit 2, which means since 2, the scaling factor is greater than 1, which means the compression will be taking place, and thus after shifting it by a 4 unit towards right, the final signal would look something like this. And then there was another expression that talked about the sum of two waveforms. So this can be done by plotting one waveform then adding the other one. So if you first focus on plotting x of 3t, so x of 3t is the waveform which is shown here in the that passes through the vertical axis, and then if you plot x of 3t plus 2, so in fact when we plot x of 3t plus 2, it comes out that it starts at the point -1 and ends at -1/3, which is the starting point of the second waveform. So it looks something like this. The sum of these two expressions is shown. Now in order to ensure whether you have plotted it correctly or not, so I talked about the talked about the shortcut in our previous lecture as well, but nevertheless I'll repeat it. So suppose that let's talk about the first example, x of 3t. So this is very simple, so this can be ensured straightforward. For example, let's talk about this example. Now the plot that I have obtained is correct or not can be ensured by substituting the values of different values at t. For example, if you look at the original waveform, the value of x when t is taken as 0 is 1, which means that inside this bracket, if the term is coming to be 0, if you feed a term 0 inside this bracket, then x of 0 is 1. Now come back to this this expression. So if somehow you make the content of this bracket 0, then x of 0 will be 1. So this content of this bracket is going to be 0 when you choose the value of t as minus 2 by 3, which means that at t equal to minus 2 by 3 x will be taking the value 1, which can be seen here. So if you are going to take t equal to minus 2 by 3, the value of x is 1. Likewise, for the original signal xt, if t is taken as 1, then x of 1 is 0. So now if we are going to choose the value of t in this particular expression such that inside the brackets we get the value as 1, so 3t plus 2 equal to 1. If you write this 3t plus 2 equal to 1, then you get t as minus 1 upon 3. So which means that t, if you're going to substitute t as minus 1 upon 3, you are going to get inside the brackets as 1, and x of 1 is 0. So this can be confirmed here. So if you have minus 1 by 3 where x of 3t plus 2 is taking the value 0. Likewise, minus 1 is the place where x of 3t plus 2 will be taking the value 0. So this is a manner where you don't need to remember the precedence rule, and if you somehow forget this, you can by this method plot the waveform. So if you have any questions related to this particular lecture, then you can post your questions or ask me on the Google Classroom today during the period during our class time. Thank you.